And it's my pleasure to introduce the last talk of today, which is given by David Beljonne from University of Mons. And he will talk about long-range energy and charge transport in conjugated polymers. So something very interesting to me. David, please go ahead.
Thank you very much, Jenny. Thank you as well to Jochen and the organizing committee for setting up this very nice workshop and for the kind invitation to talk about some of the recent work we've been doing to understand transport in conjugated polymers. So transport in solids, in very general terms, can be assessed through at least two very different approaches that are applicable to inorganic solids, where you have covalent interactions that promote long-range order and delocalized charge carriers and band transport. And on the other side, you have the organic solids with where this order is ubiquitous and charge carriers or energy carriers get localized and hop between sides. Of course, these are two extreme cases, and you can think about a continuous pathway going from the full expansion of the energy or charge carriers over many, many molecules to something that gets confined over a single molecule. And this confinement is believed to be driven by time fluctuations of either the site energy, so the energy of a charge or an energy sitting on a molecule, and fluctuations of the quantum mechanical interactions between those molecules. This can take place at different time scales, differentiating between static and dynamic disorder, and we've heard about the importance of time scales previously. So there is a very nice model that has been proposed by Alessandro Troisi and Simone Frattini. We have heard already a lot about it, transient localization model. And so I will be very brief here on this, but the very nice point with this model is that you can actually extract an analytical expression from the mobility that relates the mobility to the transient localization length that those charge carriers will explore within a given time scale that is fixed here by the time scale associated with the dominant vibrational modes that give rise to this localization. Still, it's very much a band-like model because there's a very strong impact here on the relative phase of the interactions, which is reminiscent of band theory. So if you want to go a little bit further and try to define a more universal approach, then you have to go to numerical simulations. There are different ways of doing that. You can go to a full quantum mechanical description, and we'll hear about that tomorrow with Irene Burkhart's presentation. We have decided to go to a somewhat simpler approach that is based on mixed classical quantum simulations, surface hopping simulations, so combining the coupled time-dependent category equation with Langevin equations of motion for the nuclei. And so we've also heard a lot about surface hopping, so I can be very quick here. Two important things I would like to stress: the importance of taking into account when solving the equation of motions for the nuclei for the electronic forces on the nuclei, so the back forces that give rise to the polaric effects, and also to go beyond Ehrenfest or mean field theory, at least in the case that we looked at. It turns out to be important to really use to go to surface hopping as introduced by Tully. And there are many variants with different corrections. I won't go into the detail of those, but let me show how this model works for a very simple system, which is a one-dimensional system where you have those sites that could represent molecules or polymer segments or units that are coupled to some vibrational degrees of freedom, changing the energies, and they're also coupled to another through this non-local electron phonon coupling term here. And so you can include both the local electron phonon interaction and the non-local phonon electron interactions and solve calculate the mean square displacement by solving this surface hopping model. And these are the results that we obtained for these one-dimensional models. And the nice thing about using model Hamiltonian is that you can play with the parameters. And here the parameter that is changed is the magnitude of the transfer integral between molecules, going from small value, the black data, to large values, the purple data here. And you can see that's increasing the electronic bandwidth in a way, change completely the temperature dependence of the mobility, going from a thermally activated behavior as expected for hopping and Marquis theory to a band-like behavior for larger bandwidth. At the same time, the charge extends from being, sitting on a single unit in the hopping regime to only a few molecules in the band-like regime. So you get a poor low behavior, which is reminiscent of a band-like behavior for the mobility. As soon as you reach something like delocalization over a few units. Now, going to the polymers is, of course, quite difficult, and we have heard from Jenny the very nice work she did on trying to understand the different microscopic contributions that dominate the charge carrier mobility in those materials. It's quite complex because those polymers can be prepared with very different morphologies, going from completely amorphous to most of the time semi-crystalline structures. And the issues here is that you have to cope on the one end with very large electronic bandwidth. It can be a few electron volt for hole or electron transport along the polymer chains, but very weak, a few tens of MeV transfer integrals or electronic couplings in between the chains. So very interestingly, there's a lot of work that has been done in trying to improve the degree of order in these semi-crystalline polymers, and the very nice example of that is PBTTT, where by changing the nature of the monomer units here, you can reach a density of side chains that is very similar to what we get in pure alkanes, and that ensures to get a very highly crystalline or semi-crystalline polymer sample where the chains pack in the form of stacks, and those stacks assemble in lamellar structures that interdigitate, and so that gives rise to robust structures with highly ordered, as you can see from G-wax patterns, and pretty decent hole mobilities, similar to what you would get for a number of molecular semiconductors. The surprise came when actually Ian McCullough designed this polymer IDTBT, which, even if you don't know anything about G-wax pattern, it's very clear that the very nice spots that you see in PBTTT have completely disappeared in the case of IDTBT. So it's much more disordered, almost amorphous, and still it shows a high charge carrier mobility for holes on the order of 1 or 2 centimeters square per volt second. How is that possible? The group in Cambridge, Henning Seringhaus and colleagues did a lot of work trying to understand what's going on in these polymers. It's kind of strange behavior in a way, because it shows a temperature activated mobility, so reminiscence of hopping, no hole effects, but still very high mobility, and the high mobility can be related to the low energetic disorder that those polymers show, with O-back energy that are close to thermal energy at room temperature. And without going into the detail, we showed through a detailed combination of molecular dynamics and quantum chemical simulations that those polymer chains were quite resilient to conformational disorder. So you have rather stiff chains with fluctuations in the torsions do not lead to a high energetic disorder. But still, to get percolation in 3 dimensions, you need for some close contacts between the polymer chains. Of course, you do have those contacts in semi-crystalline polymers because of the phase-phase cofacial interactions, but what about these new polymers, IDTBT, for instance? Or here's another version of, in the same spirit, it's called TIFBT. The only difference here is that we replace the donor by a slightly larger donor group. And what it primarily does is to lower the density of the alkyl side chains, because you actually increase the size of the donor unit. Now you can actually probe, and that's what is very nice, the close contacts between the polymer chains using optical absorption or luminescence. And so this is some work we did again with the Cambridge group. And so here is a very rich photophysics. I won't go through all the details, but you can see the main absorption band, which we called ICT for intramolecular charge transfer. These are donor-acceptor polymer chains. So you get an intramolecular charge transfer absorption. But the interesting thing here is that low energy site of this ICT absorption, you have what is called a pinned ICT absorption. I will come back to the label used here in a minute. So, but it's very clearly seen from photoluminescence experiments. So those states do absorb light. They have a significant radiative decay. And we looked at the way, those chains interact in the solid, simulating amorphous domains of those materials. And the interesting thing is that if you compare IDT to TIFBT and you look for close contacts between the chains, so looking at this radial distribution function, well, I mean, there's hardly any contact for IDTBT, but much larger of close contact with TIFBT. And this is because since you have extended the size of the donors, as I mentioned, you have slightly lower density of alkyl side chains, and that allows for the chains to run close to one another and see each other at some angle with respect to one another. And so this is where we see this pinned intramolecular charge transfer state. They are really present, and I'll come back to the experimental data here, much more in the TIFBT compared to the IDTBT chains, simply because of this close proximity between the chains. And those pinned intramolecular charge transfer, they're actually intramolecular charge transfer states that, because of either electrostatics or slight contribution from intermolecular charge transfer contributions, are pinned close to the crossing points. And this clearly appears on this transition density here. So these states are really fingerprints, if you wish, for these crossing points that we see in those polymers. And those crossing points are key to promote charge transport from one chain to another. Still, how can we model the transport in those materials? So as I said, it's a very complex situation. So we decided to split our study in two parts. First, looking specifically at what happens along a single polymer chain. And here, so we started with atomistic simulations done by Otello, Rossini, and Matteo Ricci for P3HT samples that are here generated in the amorphous structure. And then we set up a model Hamiltonian that is parameterized against ab initio calculations. So we calculate namely the electronic couplings as a function of angle that shows the usual cosine dependence. And we've also a good description for the classical potential energy surface associated with torsion. So torsion between the different units is going to modulate, as Jenny showed earlier, the electronic coupling between the units through this cosine function. And then we can use this Hamiltonian and do the simulation of charge transport using surface hopping. And the results are shown here. Now, again, you can be very accurate and robust with those methods. It only depends on the accuracy that you use for the parameterization. But also the nice thing with this model Hamiltonians is that you can change the parameters and see what happens, for instance, if instead of fully planar chains, you would get twisted chains. And here the difference is in the equilibrium geometry of the polymer chains that are planar, 180 degrees or 0 degrees, or twisted by something like 30 degrees out of planarity. And so if you look at the mobility versus temperature that is predicted for those polymer chains, you get completely different behavior. For the planar chains, what you get is what you expect. A mobility that is essentially show a polar behavior that decreases with increasing temperature because you have more and more scattering due to the coupling to the phonon, to the torsions in this case. And if you increase the electronic bandwidth, so if you increase interaction between the monomer units, you increase the mobility values that can reach pretty high values. If instead you have a twisted equilibrium ground state, the electronic forces drive the system back to something that is planar. And that creates formation of dynamic traps. And the formation of these dynamic traps turns into a thermally activated behavior, at least until room temperature. At the same time, also, the charge gets confined over a smaller domain of the polymer backbone. So this was on the basis of a very simple system inspired from P3HT, polytriethylthiophene. And we played a little bit with the parameters to show that if you look at mobility at room temperature versus the electronic bandwidth or the conformational stiffness for planar or twisted structures, what really matters is not really to make the bandwidth larger and larger, it's large enough, but really to make the polymer backbone stiffer and stiffer. See that there's strong dependence on mobility with respect to conformational stiffness. So as I mentioned, this is for a kind of model system. Now we look more recently, it's work by Richard Dilmoat in our group, at IDTBT. There's another level of complexity here that we need to introduce because those polymers form multiple quantum wells. So we have to include in the model the energy mismatch between the units. And if you do that, and if you simulate the charge transport along one single polymer chain, this is the mobility versus temperature that is predicted. And actually it fits very well, surprisingly well, the experimental data. So that tells us something about the origin of the activation energy that is measured in those polymers, and that, according to theory, is due to the formation of this conformational dynamic traps that is associated with a slightly twisted ground state geometry. Now it's very nice. It's quite surprising that the fit is so good, because in principle, of course, as I mentioned, the transport should be limited by the interchain motion, interchain hopping. So Richard went one step further in those simulations. So we started with a fully atomistic simulation of a large number of polymer chains. And so what he did, it was actually to build up on his surface hopping simulations and say, okay, now you have a charge that can visit a number of sites along the polymer backbones. And at given occasions, when the charge is sitting close to a nearby unit of another chain, it can hop. So this is purely hopping. It can hop from one chain to another. But the way the intra-chain transport is included in the model is actually very simple. It's just to include a dwell time, a residence time for the charge that is actually estimated from the surface hopping simulations. So essentially the charge will visit within this dwell time all the units in the polymer backbone until it can reach a favorable unit for hopping from chain 1 to chain 2. And so then if you do this, the overall mobility that you get is essentially limited by, it's a percolation problem, is essentially limited by the connectivity between the polymer chains. So the connectivity between the polymer chains is a geometrical effect. We've seen much more geometrical contact for TIFBT compared to IDTBT. And you can translate this into an electronic connectivity by counting the number of contact points for a given transfer interval. So you can see that this electronic connectivity is better for TIFBT because you have more close contact points. And you can also calculate percolation pathways and do kinetic Monte Carlo simulations of the charge carrier mobility. And the numbers that we get show that the mobility in TIFBT is a factor 5 larger than in IDTBT, which is also about what has been measured by the Cambridge group. Okay, now moving to the second part of my talk about energy diffusion, we'll move to something quite different here. because those systems are highly organized. And so these are polymers that have been prepared in the group of Jan Manners based on living crystallization-driven cell assembly. So you have this poly-3-exylthiophene chains and capped with phosphonium groups that form these really very nice nanofibers with long persistent lengths. And so that's quite different from the semi-crystalline typical regular P3HT films, where you get a mixture of amorphous and partly crystalline domains. So in Cambridge, in the group of Akshay Rao, what they did is measure using transient absorption microscopy the expansion of the wave function of the singlet excitons as you excite those fibers. And you can really watch in real time. And that's actually very similar to what we predict, from a non-adiabatic molecular dynamic simulation. You can really look in real time the expansion of the wave packet using this microscopic technique. From this, you can plot the mean square displacement versus time. And if you reach a diffusion regime, which is the case here, extract the diffusion coefficient. And this is on the order of 1 centimeter squared per second in the case of these nanofibers. This is a very large number. So to put this in perspective, if you assume an exciton lifetime of a couple of nanoseconds or less, that would translate into diffusion length of 500 nanometers. So a huge, really, exciton diffusion length that, of course, would change a bit the picture in the way you see, for instance, bulk heterojunction solar cells, but that's another discussion. The question we were asking is, how is that possible? Because this diffusion coefficient is typically orders of magnitude larger than what you measure for a normal regular P3HT sample. So what is special about those nanofibers? So to explore this, we did again the same non-adiabatic molecular dynamic simulation, surface hopping simulations, where the novelty here is to replace our nearest neighbor charge hopping interaction by the long-range Coulomb excitonic interactions that are computed using a transition density approach. So we couple the system to two vibrational modes that modulate the site energy, include a little bit of disorder. Everything has been parameterized against the experimental data and modeling for the quantum mechanical interactions. So when we do the simulations, so this is shown here. So we create a localized excitation in the middle of a stack of 300 polymer chains. Here I should mention that we coarse grain the system up to a level where each polymer chain is actually described by a single site, and that's very important. But when we look at evolution of the wave packet, you can see the expansion of the wave packet, and you can calculate the diffusion coefficient out of this, which turns out to be slightly smaller, but about the same order of magnitude compared to the experimental value. So we're quite surprised by that, especially that if you look at the inverse participation ratio that tells you how much the exciton would delocalize over these fibers, the thermal average of the IPR is close to 1. And that's normal because you have a very strong polaric effect, you have a strong coupling to the vibrations, and the excitonic interactions are quite weak. But if you look at the time evolution of the system, you can see that at some points in time, the system can extend to delocalized states, which are delocalized over a number of polymer chains. And this is where the action takes place, or most of the action takes place, where the diffusion, where the wave packet starts to move faster. So in a way, the picture is summarized here. You get this energy versus distance landscape, where at the bottom of the distribution, you end up with rather localized states, but then a few kT above, you get this delocalized excitations. And transient population of those delocalized states then help for the exciton to propagate along the fibers. So a little bit like in this case, you use the wave to surf along a rather flat energy landscape, because it's a narrow energy distribution system. You have a rather low energy disorder thanks to the special preparation conditions. So, okay, here is a movie that Samuele was kind enough to prepare. So here you really have to look at the details. So initially the central chain is prepared, is excited, and so the size of the box here tells you something about the way the excitation is localized or delocalized. Each square represents a polymer chain, and what you will see is that at some point you will see small contributions, if this works. Yes, small contributions on other chains that is associated with long-range motion of the exciton from one chain to another. And so this takes place at different steps along the dynamics and help the exciton to move along the polymer backbone, along the stack. So we've looked at a number of effects that could affect the transport of excitons along those stacks. We have looked at the influence of energy disorder. Of course, if you increase energy disorder, the diffusion coefficient decreases, because essentially the extended states are further away in energy range, and so they are not so accessible, and therefore the diffusion decreases, but it doesn't decrease that much. So we've also looked at the influence of structural defects, paracrystallinity, as we have seen in the work of charge transport, in highly doped polymers, seems to play an important role. Here, not so much, at least when the paracrystallinity is invoked here to describe fluctuations in the position of the polymer chain with respect to one another. Dynamic disorder actually helps the diffusion. It makes the system more diffusive, and this is something that you can easily understand in a hopping type of picture, because essentially you increase the number of pathways that you can follow by making the system a little bit more dynamic. But so we are still in the range 0.2 to 1 centimeter square per second. So what explains then the fact that in normal samples you have much lower diffusion coefficients? And we think this is related to long-range interactions. And so we discovered that by serendipity, by doing the simulations that you would do for charge hopping, that is to restrain the interactions to just nearest neighbors, right? And so if you restrain the interactions to nearest neighbors, this is the kind of spreading of the wave packet that you see. Actually, not much spreading occurs, and you can already figure out that the diffusion coefficient is going to be much smaller than what you obtain if you allow for the full interaction range. And this is backed up by the calculated diffusion coefficients, shown here as a function of the interaction range. And that actually shows a major, really fantastic increase as a function of the interaction range over something like 3 orders of magnitude, going from 10 to the -3, close to the centimeter square per second, if you increase the interaction range from nearest neighbors up to 6 nanometers. So long-range interactions are really key to understand the behavior of those stacks. Why is that? And again, here we need to come back to some earlier work, especially to what we did something like 20 years ago to understand how the excitonic interactions change with the size of the polymer chain. So here, if you take simply 2 polymer chains that are represented by the orange lines, separated by a distance d of length L, what you predict, if you would just use a simple point dipole approximation, is that the coupling should scale as the transition dipole moment squared. The transition dipole moment scales with the square root of the length, and so that means that the coupling should increase with the length of the polymer backbone if the point dipole approximation would be valid. It's only valid if this condition is fulfilled. And so what we actually do in our simulation, we go much beyond that, we're using a monocentric distribution with atomic transition densities, but you can also describe what happens using an intermediate level of theory, which is called a line dipole approximation, where instead of taking one polymer backbone as one single entity with a single transition dipoles, is that you can decompose this into an array of smaller dipoles, which can be confined on the monomer units or on slightly larger conformational subunits. But if you do that, you will readily realize that the interactions between the two polymer chains would involve these blue interactions, which are H-like and positive. You have two dipoles interacting like this, so it's a positive interaction like in H aggregates. But you also have a large number of these diagonal interactions that are negative and reminiscent of J aggregates. And so this positive and negative interaction, they would cancel out in the limit of infinite polymer chain. And so you can do the maths, and this nice work done by William Bafford also some time ago, showing that this coupling should scale as 1 over L. So, of course, the point dipole approximation gets more valid if you make the distance between the polymer chains larger. And so this cancellation occurs mostly at close distance. And so this cancellation, of course, will then squeeze the distance dependence of the couplings. So this is nicely shown here, where we plot the normalized excitonic coupling versus distance in the case of the polymer chains that contain 30 monomer units. These are the yellow data. You can see a rather slow decrease of the excitonic interactions. If instead you make the polymer chains smaller, or if you turn into molecules, this negative interference between positive and negative interactions would be less severe, and you get a faster decay of the coupling, as shown for the blue curve here for a shorter polymer chain. The interesting thing is that if you make the chain longer, you reduce you make the fall off of the excitonic coupling smaller, but you also make the nearest neighbor interaction smaller by about 6 times. So these are the nearest neighbor interactions. So you might then ask yourself the question, which effect is going to win? You have stronger interchain interactions for shorter chains, but they decay faster. And so here again is the singlet exciton diffusion coefficient computed for polymer chain of 30 monomer units. And if you now compare this to results obtained for shorter chains, you get this result in blue. So if you look at what happens only for nearest neighbor interaction, this is exactly what you expect based on the excitonic couplings. The excitonic coupling is larger for shorter chain, and therefore the diffusion coefficient is larger. But if you include all the long range interaction, you have this massive increase for the extensive chain, for the extended chains. And because the long range interactions are not so critical for shorter chains, this does not occur for the blue dots. Actually, there is a small decrease of the diffusion coefficient that we understand also because of the fact that if you make the chain smaller, as I mentioned, you have an excitonic interaction that is indeed larger, but is also more prompt to formation of dynamic traps, because slight variations would give rise to the formation of slightly deeper states in the density of states that tend to trap the diffusion. This is a minor effect. But so you can see that there's a contrasting behavior between small molecule versus extended polymer chains. And really, to make the transport along those stacks efficient, you need to make the conjugation along the polymer chains better. That's the message. Now, just to put this in a slightly different perspective, and I like very much this slide that I took from Greg Scholes about designing Hamiltonians for sustaining coherent effects. And so here you can describe what happens in different type of Hamiltonian using von Neumann entropy, and you can calculate von Neumann entropy very easily from density of states for different Hamiltonians. And if you do that for an Hamiltonian of that kind, where you only have nearest neighbor interaction, so this is an Hamiltonian that will be representative of charge transport. You end up with a very large von Neumann entropy. If instead you move from this Hamiltonian to this one, where all the molecules are coupled to the cavity, and that would be representative of what happens for the formation of a polariton state, well, then the von Neumann entropy is much smaller. Actually, what you have in this case is you have the low polaritonic state that is away from the high density of states associated with the dark states, and that allows you to eventually preserve coherence. So increasing von Neumann entropy means less resilient to disorder, means more decoherence and localization. And so with the polymer chains that I just showed, somehow we are in a situation that is intermediate between these two cases, because since we are suppressing or we're making the interactions long range, so we are somewhere intermediate between these two extreme cases, and that might explain why we get this transient delocalization effects to be so effective. So these are the take-home message. So from my talk, backbone conformation and resilience conformational disorder is critical for transport along the polymer backbones. No, we might end up with situations that is very similar to a situation that is encountered by people working on carbon nanotubes or even in 2D materials, where transport in those materials is limited by junction resistance. You have a high electrical transport, the charge transport within the flakes, for instance, of MOS2, but weak, but the transport is limited by the junction resistance between the flakes. And so this is something that, that we need to optimize, I think, in the case of conjugated polymers, at least in following the same spirit as what has been done for IDTBT. So singlet exciton diffusion can reach hundreds of nanometers in diffusion length, thanks to long-range interactions that sustain a transient delocalization mechanism that is somehow reminiscent of what happens for charges. But here, with the additional complexity or added value, that we have those long-range interactions that play a critical role. So with this, I would like to thank the people who have done the work. It's mostly Suryodey on the transport simulations, and Samuele, who has now joined the group, and I'm really pleased with that. But also Richat in our group, and this long-going collaboration, interaction with Vincent Lemort and Johan Olivier, who is now in Namur. And we have also benefited from a very strong interaction with Lingjun Wang, who developed the surface hopping code, but also with Matteo Ricci and Matteo Vachoni, who worked with us on the morphology of the P3HT samples, and a very nice long-standing collaboration with the group at the Cavendish, Richard Friend, and in Singinghouse, Akshay, like especially to ally the work of Sasha Snate and Sam Scott here. Polymers have been provided in those experimental studies by Jan Manners and Yin Bakalov, and many thanks for that. Okay, thank you very much for your attention. I might have a little bit long, sorry about that.
Thank you very much, Davide. So you did run over a little bit, but nobody is waiting to talk after you, and I can see from the attendance that the people who needed to go home have gone home.
Right.
So we have still got questions. We've still got plenty of people listening here. So so first question is from Oleg Karlanov, and he's asking you a question about the von Neumann entropy picture. And he's asking where you've shown different graphs of the non-interacting Hamiltonians, and has asked about what about interacting Hamiltonians in the entropy language. For example, we know that one dimension 1D is drastically different here from 2+ dimensions. The well-known, referring to the, for example, the well-known absence of phase transitions in 1D. So I'm not sure if the question makes sense to you.
Well, I would think that okay. So this is, you know, to put the thing in a slightly broader perspective, of course, and we are not really trying to follow the path of designing Hamiltonians for increasing coherence that has been proposed by Greg, but just wanted to put the things in this broader perspective. But I think that the comment that indeed the increased dimensionality could be an important factor is very relevant. You know, I see the fact that we have long-range interactions and therefore multiple pathways also for the charge to move, something that goes somewhere in a similar direction as increasing dimensionality. So in the case of this one-dimensional stack, I mean, they are one-dimensional, so there's not much we can do about that. But the long-range interaction somehow has an effect that would be similar to the effect that, for instance, you would expect in a molecular crystal that you can grow in 2D or in 3D. So indeed, I mean, there's a lot of, I mean, it's the same kind of ideas, I would think, yeah.
Okay, thank you. The next question is from Sergey. David, thanks a lot. In your energy transfer surface hopping modeling, how sensitive are your results to the way that you treat frustrated hops that are driving system up in energy to more delocalized states?
So the approach that we use has been developed by Lin Jun and includes all possible corrections that need to be introduced in the model to get reasonable results, and that includes, of course, the exclusion of trivial crossing. That includes also a proper decoherence, and so the approach has been tested in some well-defined conditions, in some well-defined cases. We've seen in the beginning how it can reproduce the crossover from hopping to band, and so in that respect, I really trust the approach is robust. And is robust enough to describe also what's going on in the case of Exciton transport.
Okay. Last question from Jochen. In the case of the energy transport in the nanofibers, is exciton transport limited by excited state reorganization energy, and how large is it?
Yes, in a way, because well, the exciton reorganization energy, I don't have the exact number in my head right now, but it's on the order, it's the typical value, let's say 100 or 150 MeV. So the thing is that compared to charge transport, this is now much larger than the excitonic interactions, at least the nearest neighboring excitonic interactions, which are only on the order of 10 MeV. Yeah? And so typically this is a situation where you would expect the excitons to be completely confined, to be completely confined in space. And indeed, if you look at a time trace of the trajectory and you do an average of the participation ratio, this is what you get. But it doesn't prevent you to go at least in a transient way to have access to these more extended states. And this is this transient delocalization, the surfing over the wave that allows you to move faster than what you would predict based on simple Förster or simple hopping based mechanism.
Okay. There's no more questions on the chat. If I may, I might ask the question myself.
Sure, Jane.
Also on the same area, which is just whether in the treatment of the kind of the surface hopping applied to exciton transport, how sensitive is the finding to the degree of order, the degree of long range order in the structure?
Yeah, that's a very good question. So this is something that I went very quickly on. So we have this slide where we looked at a number of different possible effects that can change the diffusion of the singlet excitons. So we looked for sure. So there is a little bit of disorder that we put in the model, energy disorder, that is taken from a Gaussian distribution, fitted against the experiment. And so if we tweak this number, of course, this has an effect on the diffusion coefficient as expected. The thing that we did is to change also the positional disorder in either a static or in the dynamic way. So in a static, that means that we are moving the chains closer or further away using a cumulative transport, similar to what has been used in the talk of Henning to simulate charge transport. So we have an inhomogeneous distribution of, let's say, interchain distances, and that doesn't seem to affect the transport. Actually, you know, Suryo was also doing some experiments or numerical experiments where he was taking out some of the chains. You know, he was completely removing some of the chains from the stack. And I was really shocked by the results because the diffusion coefficient did not seem to change very much when you were removing chains. So essentially, because you have this long range effect, it's a little bit like, you know, in a way, a variable range hopping type of mechanism, where depending on the energy landscape, you can go over large distances and cross defects. Yeah.
So the large Ds don't require long range order.
No.
Right.
No. I mean, it's you have to, yeah. Okay. It's a bit tricky because you could say from simulation, the large D does not really require large range order. But if you don't have this long range order, you will also introduce disorder along the polymer chains, right? And this is something that was nicely shown by actually by Gabriele Davino when he was doing his simulations for transport in the highly doped systems, is that so the paracrystallinity, for instance, would change the distance between the chains, and so that has an effect by itself. But the most important effect is indirect. If you make the chains further apart from one another, there will be on average more disorder each of them separately. So intrachain disorder will increase, and that would have an impact on transport for sure. So you see the effect is there, but it's a bit indirect.
Okay. Okay, great. So I think that exhausts the questions in the chat. And I think we should, I would just like to thank all of this afternoon's speakers again, or all of this session speakers again, Marcus, Davida, and our 5 super lightning talk speakers who all managed to talk, give their story in 5 minutes. Very impressive. And thank you very much, and have a good evening, and see everybody tomorrow.